Hello everyone. I hope that all of you are fine. Welcome to another lecture of robotics. In this lecture, we shall learn about motion planning. So let's begin. So in today's lecture, we shall first discuss about motion planning. We shall define what is motion planning and how it's different from path planning. After that, we shall today learn about the types of motion planning problems. Then we shall talk about motion planning methods, different kinds of methods like grid-based methods, graph-based methods, and some other different types of more methods. Then we shall talk about the properties of motion planners. These properties they overlap with the performance parameters of algorithms that we have studied in the previous lecture. And then we shall learn today about the graphs. What are the graphs? What are the trees? And different types of graphs we have and their properties. And then we shall learn about the grids. Then comes the grid search methods. We shall today learn that how we can search a target position within a grid, how we can find a path within a grid. So this will be a very important topic regarding motion planning and path planning. And then we shall learn about different types of graph search algorithms. Breadth first search, and then Dijkstra's algorithm, A-star algorithm. So let's move on. So before starting this lecture about motion planning, I want to just remind you about the previous a slide from the previous lecture in which we discussed about mobile robots and autonomous navigation. So if you remember, we talked about that for autonomous navigation by a mobile robot, we need these are some of the basic components a mobile robot is expected to have. So here's an environment. Then using sensors, the robot builds its perception about the environment, how the environment looks like, what's going on in the environment. And then we after that, if you remember, we discussed about localization. We talked about odometry. We talked about the localization using landmarks. And then we talked about mapping, especially the discrete maps. So till here, we already covered in our previous lecture. And today we shall be focusing on motion planning. It's not explicitly written here, but motion planning is, you can say that these two blocks, when you combine them, it's called motion planning. It's motion planning. It comes under motion planning. So first is the path planning. In path planning, the robot plans a path to the target position where it wants to go. And in motion control here, the robot follows the path and the robot tries to control its its joints, its motors, speed and position to follow the path and to control its position. So today's lecture will be this motion planning portion. We shall not discuss about this thing here. This is mainly the control problem, so we shall discuss this later. But for today, we shall be discussing this path planning. Mostly how we can do path planning and how we can what are the different types of the algorithms available. Okay, so let's see what is motion planning. By definition, motion planning is a problem of finding the motion of the robot from start stage to goal state that avoids obstacles in the environment and satisfies joint limits and torque limits. So in simple words, you can say the motion planning means the motion of a robot from its start position to the target position by avoiding the obstacles. So let's say this is the start position of a robot, and here is our robot, and this is the target position. So there are some obstacles in the path. In this environment, there are some obstacles here. So the robot is, so how the robot will move from here to the target, avoiding the obstacles and reach the target. Okay, and also it should satisfy the dynamic constraints. For example, if there are some limits on the powers to the motors of the wheel. So it has two wheels here, let's say it's a two-wheel robot, and both wheels have their own motors. Okay, so the controller of the robot, while following this path, it should also know that what are the maximum limits of this of the torque here that should be used by the motor, and also the limits regarding the joints. For example, how this robot can move in sideways. For example, if the robot wants to move in this direction, so how it can move in this way, and how far it can go in this way. This joint thing is mostly common in the robotic arms, especially, for example, if this is a robotic arm, let's say two-link robotic arm here. This is its fixed location, and this is the second joint here we have. So this is the joint J. So it has limits of, let's say, this joint. It has limits. So the motion is limited. So the during motion planning, what we consider is that we consider also what are the limits of these joint angles, and how much force is required here, and what are the limits of these forces here. Yes, so this is motion planning. Okay, every point in the configuration space or C space corresponds to a unique configuration Q phi 1 to phi n of the robot. So when we talk about configuration space, we say that an area, a space, okay, and we call it configuration space or a C space. And so the idea is that every point here in the configuration space, let's say this is point P1, point P1 correspond to a unique configuration. Q is equal to, so these are the phi 1, phi n are the angles of the robot. Okay, so if we have a robot, for let's say if we have a industrial robot, let's say we have here, and this is the link 1 and this is the link 2. So you can see that this angle is phi 1, and this angle, let's say this angle is here is phi 2. So these are the these are the angles corresponding to this configuration P1. So this P1 point can be reached by this configuration of the robot. Okay, let's say you can say like this. Okay, P1, we can achieve P1 if we have angle phi 1 is equal to, let's say, 30 degree, and angle phi 2 is equal to 45 degree. So then we can reach this P point. So yeah, so this whole area is called the configuration space we have here. And now we have something else, it's called free configuration space. And for example, if there is an obstacle here, then of course now this free area, white color area, this will be the free configuration space, and this can be represented by C free. This one here. Okay, so this is C free, and now the robot can only have its position anywhere in the free configuration space. It's not allowed to go this in obstacle configuration space. Okay. Geometric model of the robot and environment is available. Yes, for motion planning this is important. The geometry, we should know that how the robot looks like, because let's say if we want to park a vehicle let's say we want to park a vehicle, we have a car, and here is one car, and then here is another car here, let's say, and then I have a third car here. This is C1, C2, and then I have here another my robot, let's say a car-like robot. Okay, this is my robot, and I want that the robot should go here, and the path is like this. Let's make this a little bit bigger. So okay, and the path is, let's say, the path planning algorithm or the motion planning algorithm. It says that okay, go here and then go here. Okay, but of course for parking between these two cars or vehicles, it's the car cannot simply go like this and then park here. So what it do is that it will have some kind of complex motion. For example, first it will go here straight, and then it will reverse, and then after reversing it will turn here slowly, and then finally it will get straight and park here. Okay, so for all these complex motion, we need the geometry of the robot, and also the environment, also how the environment looks like, how many other obstacles we have in the environment, and what's their geometry also. Okay. Types of motion planning problems. So now we shall see that what are the different types of motion planning problems we have. And so the first one is the path planning versus motion planning. So what's the difference? Actually, the path planning is you can say, a subfield of motion planning. Motion planning is you can say a broad term in which there is a path planning involved, path following involved, and also position control or velocity control. But path planning is only focused with finding a collision-free path. Next we have control inputs. So again, this is another type of problem in motion planning, is the how the inputs to the robots should be controlled. Okay, for example, not all robots can change their direction instantaneously. For example, we have studied for example, a car-like robot. Let's call it CR. A car-like robot, when goes like this straight, it's easy, and when it want to turn, then it can turn like this, but it cannot turn instantaneously in other direction. Like it cannot go instantaneously this way. Okay, so let's say a path planner has draw the path. The path planner says, okay, you have to go at this position here. It has to go at this position, this car-like robot. So what it will do, it cannot go directly here. No way. It can go in this way, but again, it has to do some kind of, to reach at this position. It can either go this way and then here, go this way and then come backward here, reverse, okay, and then reach this position. So all these the control of the motors of the steering and the driving motors of the wheels, these control inputs, okay, I say these control inputs to the driving velocity and also the steering of the wheels. Motion planning is also, so this is another type of motion planning problem where you have already a path available, and now the problem is you have to follow the path by controlling the velocity and the angular position of the motors, or their velocity and torque. Okay, another type of problem is the online versus offline motion planning. So if the environment is dynamic, if you remember from the previous lectures, we have studied about the dynamic environments where the obstacles are changing and they represent like a real world model where there are new obstacles, unexpected obstacles. And so when the robot encounters these types of environment, then it needs online motion planning. Okay, online means the planning is being done online at the same time while the robot is moving in the environment. Okay, but the offline means the planning was already done, the environment was static, the obstacles were not moving, and so once the motion planning was done and it generated a path, it said, okay, move from this position to this position to target position. Okay, and then the robot just, once the path is generated, the robot just follow this path. Okay, so but the motion planning was done before, offline, but the path following was done later. Okay, but in the online case, both the path planning and the path following of the obstacle avoidance, they were being performed at the same time. Optimal versus satisficing. So motion planning problems can require sometimes the optimal results. Optimal means the best, either the maximum or the minimum. For example, the maximum they require the maximum, you can say, output. Okay, and they have the minimum time or the minimum energy requirement. So motion planning problems can be you can say that to calculate some kind of optimal solution. For example, if I want to move from this location to, let me change the color with red. Okay, so from here there are some, this is start point, there is an obstacle here, and this is an obstacle here, and this is my target point here. This is the start point. Okay, so now the problem can be, optimization problem can be like this, that you have to find a path. There can be, you can see there are multiple paths to the target. This one will be, let's say, this one will be shortest path, let's say. Another path can be here. This one can be, you can say, longest path here. But then, let's say my goal is to minimize energy consumption. Okay, I want that the robot should move from start to target position with minimum energy or with minimum fuel. So which path will be best? So maybe this time the using motion planning optimization, it will follow a different path to save the fuel. So yes, so this is another range of problems that also are covered in motion planning. Then we have exact. Okay, I forgot to mention about satisficing problems. So in optimal problems, we try to find the best best solution, like best path for time saving, best path for energy saving, or the path with shortest length. But in satisficing, we are not concerned with the best. We are not concerned with the maximum or minimum. We are concerned with at least a path that satisfies some minimum requirements. For example, in this example, we shall try to find a path that just avoid obstacles and reach the target. So this is enough for us. It's not optimal path, but it satisfies at least some parameters or some you can say performance measurements, you can say. Then we have exact versus approximate. So we already covered this thing, I think, in the algorithms. So in exact type of problems, we have to find the accurate solution, okay, to the problem. For example, I will give this example like this. This is a start position, this is the target position, and the robot reaches somewhere okay, this is the target position, and the robot path is like this, okay. But the actual path is something like shortest path is like this. This is the exact solution, okay. But the robot doesn't follow the exact solution or the accurate one. It has some errors, some fixed level of error in the path. So then it will be an approximate solution, okay. So this is the difference between exact and approximate. And then finally we have with or without obstacles. So motion planning, it's a challenging problem, and it can be with obstacles or without obstacles. With obstacles, it will have a different demands, and without obstacles, as you can see, there will be different kind of demands. For example, the motion controlling the motion of the robot, and you can say finding the optimal trajectory. So these kinds of problem we will face in this category. Now we shall see the motion planning methods. How can we do motion planning? So we have grid-based methods. Grid-based methods, they decompose the environment into small cells, or you can say they discretize the environment, okay, and then they use motion planning or path planning, you can say. So these are grid-based methods that works on discrete environment. They make a grid, or they make they discretize your environment. Then we have complete methods. They include visibility graphs. They have a different approach solving the problem, and we shall see later how they work. We have sampling based methods. They use sampling to get different points on the configuration space or in your environment, and then so these samples are randomly generated samples, and then they try to join these points and Yeah, so they also try to find collision-free path while satisfying some constraints. So we shall study these methods in detail in upcoming lectures. This is another motion planning method using virtual potential fields. So in this method we have artificial potential fields. So there are some attractive fields. For example, there is a target here and start position here, and then we have obstacle here. So your robot will start, and it will be attracted to the toward your target. The field will be attract this robot toward the target, but this obstacle, it will repel this robot away from the target. And the detail we shall see later. And then we have nonlinear optimization. So this is a totally different approach to solve the motion planning problems. In nonlinear optimization, the path is generally represented by some kind of polynomial equation, and then we try to optimize this equation to either minimize or either maximize the cost function, and also we satisfy the constraints on the controls and obstacles. So we shall see in the upcoming lectures, we shall see the details about this. So properties of motion planners. What are the important properties we have here? Multiple query versus single query planning. So this is one of the property we have. Some algorithms, they are multiple query, and some of the algorithms, they are so let's say if this is our start position and this is the target position, and so these are some intermediate points we have here within this space. We have some other points also. Okay, so what the single query planning algorithms, what they do, they only one time they try to find the shortest path between the, let's say, the start and target position. It's not shortest path, but let's say it's satisfying some other kind of criteria. So the robot must visit also these points. So this is, you can put this criteria. Okay, so the robot should visit this 1, at least 2, 3, 4. So the robot should at least visit 2 of the points. Okay, so let's say this is the criteria we have. So once this target is achieved, the target is found and the path is found, then these algorithms are complete, they're finished. But multiple query algorithms, they are for many times, if the robot has to plan pass to the multiple targets, then multiple query motion planners will be helpful. For example, the multiple query algorithm, what they do from the beginning, they will calculate the shortest path from every angle, from every possibility they have. And it will be quite complex. So they will try to find a path from every point to all other points, shortest path, okay? And later, if let's say if the user want to have a shortest path between this point 3 and a target, then they have already calculated this path, okay? Initially they have already calculated. So these types of algorithms, they are useful where there are multiple targets, okay? And yeah, but if there are not multiple targets, there is no then there is no use of calculating the shortest path of every point to every other point. Then it will be resource expensive. It will not be efficient. Okay, then we have anytime planning algorithms. Anytime motion planners or motion planning algorithms, they keep improving their solution or output, okay? After they find an initial solution. This is a property of anytime planners. For example, let's say this is a start point and this is our target point, and so this, if the algorithm is something like anytime algorithm for motion planning, initially it will quickly try to find a path and reach the target point, okay? But with the passage of time, it will try to improve this path. For example, if the requirement is to find the shortest path, then after some time it will make this path like this, and then after some time it will make path like this, and finally after some time it will find this shortest path, okay? But it has already found initial path also. So these types of algorithms, they can be stopped after a certain time, or any time, you can say. That's why they call anytime algorithms. So they can be stopped anytime, and they will give you some kind of solution. So if you stop them late, it means they will give you a better solution. If you stop them early, then they will give you maybe some solution, but it will not be exact or optimal solution. Completeness. This property we already studied in the algorithms. Completeness means the algorithm or the motion planner will find a path if there exists. Okay. In the algorithms, we studied completeness with respect to a general perspective, but here we will study the completeness with respect to path planning or motion planning. So let's say we have the start point, and then this is some kind of room. So target point, and this is obstacle we have here. So if the algorithm is complete, then it will find the path. Okay, if the path exists, this we will call a complete motion planner or complete path planner. Okay, but what if there is no path? Let's say it is blocked. This whole area is blocked. Then in this case, if the algorithm is complete, it will try to search the path, and if there is no path exists, then it will say no path exists, and it will fail just, okay? But it will tell you that there is no path to the target. There are some other kinds of algorithms that are not complete motion planners. So what these types of planners they do, even the path exists sometimes, okay? Even the path exists, but they fail to find. For example, start, this is target, and I will make it a little bit more complex this time. Okay, if the algorithm or the motion planner is not complete, so it will try to search path, and once it don't find path, it will fail. Even the path exists, the solution exists, but it's unable to find it. So it means they are not complete. There is no guarantee that they will find a solution or a path always. Then we have computational complexity. This we already also discussed in algorithms in our previous lecture. In computational complexity means how much time and space is required by algorithm to find the solution. So this is computation related to computational power. Okay, so there are motion planners that are very fast, and they also require very less space on your memory. But there are other types of algorithms that are not so fast, and they require a lot of memory. So this is also one of the property of the motion planners, and it's very important, especially when you want to do online motion planning, and you have limited resources, you have a limited battery, limited small embedded computer, a limited memory, and also you have to react very fast to this dynamic environment. So it means that then you have to consider this property, and it's very important. Okay, we studied motion planning. Now there is a subcategory of motion planning, and it's called the path planning. We shall see this in more detail. What is path planning and how we can do path planning. So this is purely a geometric operation, path planning. And in path planning, what we do, we find clean free path from start position to target position. So this is a start position, and this is target position, and then there is an obstacle. So what we do, we try to make a path that the first is that it avoids the obstacles and reach the target. Okay, this is one of the requirement. And then we have satisfy some constraints. The constraints can be like, for example, the robot has a limited battery, and then we have to be careful that our path should satisfy the battery constraint. So the path should not exceed the battery constraint. So if I want to go from, for example, one city to another city, I should have also I should also consider the fuel in my vehicle, and also choose the path that satisfies my fuel constraint. By the way, what the constraint means here, the limitation. Okay, constraints mean limitation. A robot has a limited battery. It cannot travel infinitely distances. It has a limited battery, so it can travel only a limited distance. So here there are many types of path. It can be like this path here. It can be like more closely like this path here. So the robot should also the one thing is it should find a collision free. Collision free means it should not collide with this obstacle here. There should be no collision. The robot should avoid this obstacle. Okay, this is obstacle. So the first point was the robot should reach the target without collision with the obstacle. And the second point is it should also satisfy some limitations. I gave you an example of the battery. If a robot has a limited battery, we should select the path. The robot should select the path that is coverable within this amount of fuel or battery energy. So what we do here, you see that whenever I say robot, I draw a point here like this. I say this is a robot, but actually robots they have a different kind of geometry. They have shapes. Okay. So, but in path planning, I am allowed to do like this. I can make a point. Okay. I can say that this is my robot. This is my vehicle. And the reason is that because path planning doesn't require the dynamics or the equations of motion of the robot or the shape of the robot. Path planning is purely concerned with finding a collision-free path from start to target position, avoiding the collision with the obstacle, and satisfy some internal constraints. But it's not related to geometry, so that's why what we do, we can take the robot as a point. But my actual robot may be something like this, with some wheels here, one wheel here, with some kind of sensor here. Yeah. So I can represent this robot with a point here. Okay. So now the question is that if I represent the robot with point, how it will actually avoid the obstacles. For example, this is my start point and this is my target point here, and so these are the obstacles here. This is the obstacle, and this is the second obstacle we have here. Okay, so let's make it like this, like a room. Okay, so the robot want to go from here to target, and the thing is, here I have only, in path planning, we have only considered robot as a point, and when we say that robot, we have found the shortest path, we say that okay, we are only concerned about the path, we are not concerned about the size of the robot. But actually, in reality, let's say this was a path of the robot that my path planning algorithm have made. Okay, and now the robot actually want to follow this path, but the robot looks like a little bit bigger. Let's say the robot is like this. So can this robot move here within this path? Of course no, because the robot is bigger, and here this area is smaller here, this area. So the robot cannot go here. So for this purpose, what we do that when we take the robot as a point, we make obstacles a little bit bigger also, so that they represent the actual size of the robot. So it's called obstacle inflation. We inflate the obstacle, we make the obstacle bigger proportional to the size of the robot, the radius of the robot. Okay, so what we do now, our obstacles are like this, and now when I move this point from here to here, so there is no space, so it means there is no path here so there is no path, a path doesn't exist. But when we do motion planning, then we have to consider the geometry of the robot, how it looks like, what are its dynamics, how much friction is there, what are the angles, limitations, how much force it can generate, what are the limitations on the force. All these parameters we have to consider in the motion planning. Then we have optimization. This we have already covered, that optimization means to minimize or maximize some parameter, for example, to minimize energy, to maximize speed, or you can say to minimize the length of the path. So all these things are also involved in path planning, and it's a special field. It's called optimal path planning, but it's out of the scope of this course, so we shall not go in the detail of this. Okay, till now we have discussed about motion planning and path planning. We talked about different types of motion planners, their properties, but now we shall actually going toward the path planning and how it works. Before doing path planning, we need to understand some basic concepts, and one of these concepts is graphs. What are the graphs? So the definition says that graph is a collection of nodes, vertices, and edges. So it means a node. A node means any point with some coordinates, x, y coordinates, and let's say this is x1, y1, and then there are some other points, x2, y2 coordinates. This is my point A. I call it node now, and this is B. And if I join them with some kind of line, okay, let's make one more, sorry. And this is my C point C. This is x3, y3. So now if I join them with line, what will happen is that Now this is the whole collection of these nodes. I call these points as nodes now, or vertices. Okay, nodes is the most common word. So these are the A, B, C are the nodes, and these green color lines that connect these nodes, they are called edges. Okay, and this collection of whole thing, it's called a graph. So I think I should change the color, otherwise it will be confusing. So this whole thing, collection of all these nodes and edges, so this is called a graph. Okay, so that's what graph is. It's you can say a collection of points and lines. A node represents configuration or state. So in the graph, what node means a configuration or a state of the system. Nodes are joined by edges. Okay, and that we have already covered. Edges indicate the ability to move from one node to neighboring node or adjacent node. So if the robot wants to move from point A to point B, it means it can only move on this, using this edge, from this point to another point. And also one more thing is that it's these edges are always straight. They are straight, they are not curved. So here I made a little bit, I think, non-straight, which is kind of misleading, but this is not the case actually. They are perfectly the straight ones here. I shall try to make them straight now. Okay, better than before. So yeah, so it means a robot want to move from A to C, it can only go on this green edge, but it cannot go from C to B because there is no edge between C to B. There is no connection between B to C. Okay, so this is the concept of graphs, and they are very useful in networking. Networks, for example, in planning networks, in road networks, they are very important. Okay, what the graph does actually, in our case, the graph actually models the free space in your environment, or in the map, you can say. It can tell you where is the free space and where you are allowed to go. For example, in this case, in this graph, let's say there was how the graph modeled the environment. So it can say that the robot can go from A to C, the robot can go to A to B, but robot cannot go from C to B, because the reason is that there might be an obstacle here. Okay, which was not shown before, and also the robot cannot allowed to go here, other places also, because let's say the surface was not smooth or something. So the robot is only allowed to go at these positions. So yeah, so What model means? Model means to make a mathematical equation that mimics your environment, that shows the behavior of your environment. Okay, if you want to show that where the obstacles are in the environment, then you have to make a discrete map. Okay, if you have to show that where are the free spaces where the robot can go, then you can represent this thing with the help of a graph. So now we have types of graphs. How many types of graphs do we have here? We have directed graphs or undirected graphs. The first thing, this one here, directed or undirected. So what's the difference between directed and undirected? So let's take an example of the last one. This is node number A, this is node number C, and this is node number B. We have 3 nodes. Okay, if there is some kind of arrow like this on the edge, there is an arrow. Again, I forgot to change the color. Okay, now this is an edge. If this edge has an arrow, it means the graph is directed. If the edges, in the graph, if the edges have arrow or the direction, it means the graph is a directed graph. There is a direction. It means the robot can move from A to C, but it cannot come from C to A back. And same is true for A to B also. The robot can move in this direction, but cannot go back. But there is another condition also. For example, if the graph have multiple edges, for example like this, it has 2 edges. In this case, the robot can go and come back also. Okay, but the graph is still a directed graph, because here it has, because all the edges have some kind of direction associated with this. And also there are undirected graphs. Undirected graph we have already studied in the previous slide. So if the graph doesn't have the arrows inside in it, the edges don't have any direction, it means the graph is the directed graph. So this is the example of this is example of undirected graph. Undirected, undirected graph, UDG, and this is an example of directed graph, DG. Okay, I hope that this is clear. It was not that difficult. Next we have weighted or unweighted graph. So if the graph has, for example, let's say graph has nodes A and B, these are 2 nodes it has, and then we have the edge, and the edge has some value on it. Let's say this is 5. Okay, then it means that the graph is weighted. Weighted means it has some value on this graph. Let's say the other one is, this is 2. So it means that going from A to B, it costs you 5 units. It can be anything, 5 meters, it can be 5 liters of your diesel, and from going from B to C, the weight is 2. It means 2 can be anything, a distance, a time, energy, fuel. So this is the weights on the edges. So if the edges have weights on them, it means the graph is weighted. Okay, but if the edges don't any weight, it means the graph is unweighted. So for unweighted graph, I give this example again here. This is again an example of unweighted and undirected graph. Okay, the graphs, we have covered them, and now we shall see different types of graphs, and they are called trees. A tree is a directed graph. It's also called a digraph, in which there are no loops or cycles, and each node has only one parent node. So now we shall see a special type of graphs. They are called trees, and they look like this here. They have one parent node here, okay, and then this parent node has some child nodes, and this is always directed. It's not the other way. So a parent, and the arrow, the arrow means this is the child one, okay, and then we have this again. So this node was, let's say, parent node was A, and this is B node, this is C node. B node have again D and E nodes, and C node has only, let's say, one single node, F. So this is you can see this is a directed graph because it has arrows on the edges. Okay, these are the edges. These arrows are the edges that tells you which node is connected with which node, the combination of these nodes. So this is a directed graph or a digraph, as is clear, okay, but it has a special arrangement. The arrangement is that there are no loops, okay, so none of the node is connected back to the previous node. So there is a hierarchy. For example, this is the topmost node, that's called a parent node, or it's the root node. It's called the root node or root node. And parent and child, they are relative. For example, this was a parent node. It's also called the root node, and then these two, B and C, are the child nodes of A. Okay, and A is the parent of B and C. So this is two-way. A is the parent of B and C, and B and C are the children of A. You can say like this, okay? So it means that every node will have only one single parent. This is one of the important property of the tree that makes it's a special case of a graph. It's a tree-like structure. So every node, and it doesn't matter whichever you pick, either this D node or E, you will see that every node, each node have only single parent. E has only single parent, B, but a node can have multiple children. For example, B node has two children, D and E. Node C has only one children, that is F. But if you look other way around, F has only one parent, E has only one parent, D has only one parent. So parent will be only one, but it can have multiple 2, 3, 4 thousands of children. So this is a tree. It has one root with no parent and leaf nodes with no children. So it means that this is one more thing to recognize, that either you're dealing with a graph or a tree. If a node, it's a leaf node, they are called leaf nodes here. These nodes, 1, 2, 3, they are called leaf nodes. So these leaf nodes will not have any children, okay? And this node is called the root node. And the root node has a property that it will not have any parent. So this is how you can differentiate between a graph and a tree. To be honest, that a tree can be easily recognized because it looks very in a structured way. It has a directed hierarchical structure. So with practice, you will learn the difference between a graph and a tree. Okay, till now we have studied graphs, and we said that graphs are important for path planning. We shall use them later. We studied graphs, we studied trees, and now let's see what are the grids. Actually, grids we have already studied in the previous lecture, where we discussed the discrete maps. You remember that? We made a discrete map and we discretized the environment, something like this. There was a room, 2D room, and then we discretize it into cells, and then we call it a discrete map. So this is a grid. What grid is? Grid is either a 2D or 2-dimensional or a 3-dimensional, you can say, a structure which has cells, which consists of cells. It can either be a square or rectangular, any shape it can have. So this is called a grid. Okay. And what's the purpose of the grid? The purpose of the grid is that it discretizes your environment, 1, 2, 3, 4. And once you discretize it, it means that it's easier to work with computers, because it can be seen as a matrix, which can be used for in MATLAB or any other kind of software for operations, digital operations. Okay, in the grid we have we need to understand some more things, and one of them is a neighborhood. Neighborhood means neighborhood of the grid means how many neighbors it has. Okay, let's say this is a grid cell. I'm taking from here, and from this grid I take it. Okay, let's take up this middle cell, this one here. This cell, if it has only 1, 2, 3, 4, it's not that perfect, but if this cell C has 4 neighbors, if we consider only 4 neighbors, okay, like this 1, like this 2, 3, 4. So these 4 neighborhood is something called Fon Neumann Neighborhood. Okay, in English it will be maybe Von Neumann, but I suppose this is a German name, so Fon Neumann. Okay, anyways, so this type of neighborhood has, in each cell, it is connected to 4 other cells. If you see in this grid here, if you consider this Fon Neumann neighborhood, then this cell will have 1, 2, 3, 4 neighbors here. Okay, and same is true for every cell. Unless it's like on the side of the grid. I mean, most of the cells they are 4 connected. This is called a 4 connectivity also. Next important thing in the grids is the Manhattan distance. So when you consider 4 neighborhoods or 4 connectivity, then the distance you calculate between 2 points, let's say P1 and point P2, the distance will be Manhattan distance. So let's say x1, y1, this coordinates, and x2, y2. So if you want to calculate the distance between these 2 points, let's say these are the distance between 2 cells. From here, this was cell number 1 and cell number 2. Cell number 1, cell number 2. Actually, they are connected. So, okay, they are actually connected. So let me make them connected. Okay, so you want to calculate now, you have grid cells and you want to calculate the distance between 2 cells. This is, let's say, P1 cell, this is P2 cell. And so the distance between them you can calculate simply by x2 minus x1 and then y2 minus y1. So this will be the distance between these 2 points. There is another type of the neighborhood, and we call it Moore neighborhood. In Moore neighborhood, what we have, each of our cell, it has 8 connections. Let me show you how. This is our cell. This is a grid, okay? From this grid I've taken this cell. And this is the neighborhood number 1, neighborhood number 2, neighborhood number 3, neighborhood number 4, 5, 6, 7, and 8. You can see there are 8 neighborhoods we have in this type of connectivity. We have 1, 2, 3, 4, 5, 6, 7, and 8. But in previous 4 connectivity, we only had 1, 2, 3, and 4. we only had 4 neighbors. Okay, but in this type of connectivity, we take all the possible neighbors we have in a 2-dimensional grid. So this is more realistic. So actually, in the previous one, in the 4 connectivity, we were ignoring some of the neighbors. Okay, but here we are taking all the possible neighbors we have, and this is more realistic. And when we take this type of connectivity, then we also have to take this diagonal distance. For example, let me make with some other color, maybe green. Yes, green will be better. So we have now, previously we had only, in the previous one, we only have, you see this straight types of distances, P1, P2. For example, the x will change and y will remain same. And if you go to other side, for example here, your y will change but x will remain same. But in this Moore type of or 8 connectivity neighborhood, we have something Euclidean distance. This is because here we have also diagonal distances. See that between C and 3, the grid number, the cell number C and 3, we have a diagonal distance. So in this case, when you have a diagonal distance like this, this is your P1, this is your P3, let's say, then the distance can be calculated using distance formula, which is d is equal to under root x3 minus x1 square minus, plus y3 minus y1 square. So these are some concepts related to grids we have. So yes, let's move to the next slide. Now in the previous slides, we have studied graphs. Then we studied what is a grid and what are some parameters of the grid. And now we shall see that actually grid can be represented as a graph. Let's see how. So we defined that what was a grid. We said that a grid is discretization of a space into into cells and the cells can be of any size, any shape. Okay, it can be rectangular. So this was we call it a grid, and these we call them here, this is a cell, and let's number it. This is cell number 1, 2, 3, 4, and in this direction we have 4, and this direction we have 1, 2, 3. We have 3 here. Okay, so this is a grid. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 cells inside this grid. Okay, or you can say this grid is made up of 12 cells. And now for path planning, for example, if you want to search a path from one cell to another cell, how can we do that? How can we do that? One way is that we can represent this grid as a graph. I will show you how. How we do that is, in the center of each of the cell, we take a node. You say here is a node, then here is a node, here is a node, here is a node, and we make nodes in the center of every cell. And then what we do is that we connect these nodes by edges. So it depends upon you whether you want a 4 connectivity or you also want a full 8 connectivity. So it depends upon you. So I shall only make here 4 connectivity. And so this is our graph. This red color is a graph because it has nodes and edges. Okay. And the green color is a grid. So I make the graph once again here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So by connecting these nodes with the edges using 4 connectivity, it means that each node has 4 neighbors, like we studied in the previous slide. So we can say that this is a graph. And this graph represents this left hand side grid. So this is a graph. And this on the other side, the green color, we have a grid. So here in the graph you can see we have here the nodes and the edges. And which type of graph is this? If you can remember, this is edges E and this is node, let's say node N and edge E. Node N1, edge E1. Okay. And similarly it's true for this one. It will be node N12 and E12, edge 12. So this is undirected graph. This one is undirected. And yeah, this is how we can represent a grid in the form of a graph. Okay. So you can say a grid is just a graph that is properly organized in a specific manner. Okay. If a graph has a special order and a special order of connectivity and arrangement of the nodes, then it can be called as a grid. Or it can represent a grid, you can say, in a better way. I hope that this is clear. So next, move to the next page. Grid search. The whole purpose of our previous discussion and learning was to search a path from one point to another point in an environment. That's why we were studying the graph, the grids, because we wanted to represent the environment. We want to make a model of the environment. Okay. So we can search a path from start position to the target position, avoiding the obstacles. So this was the whole point. This was our goal. So now we are on the point. So grid search method, we have, let's say we have a grid here, let's say we have a room here. This is a map of the room, okay, and in this map we you remember the map we made in the previous lecture, the discrete map. So this is same kind of map. Let's say this is a map we made, and 1, 2, this is a discrete map, 3, and here is 1, 2. So this is a discrete map in which we have, let's say, an obstacle here in the, here we have obstacle, and you remember how we represented the obstacle? Obstacles were represented by 1, okay, 1, and we represented the free space by zeros, 0, 0, 0, 0. So these all are free spaces. And we represent the goal by 2. This is our goal. And okay, let's make this map a little bit bigger. Okay, so zeros are the free spaces, free cells. 1 means here is an obstacle, and you should also fill here free space. And the goal, we call the goal, is represented by 2, and again the free space is by 0. And this is start position, and let's say it's represented by S. So this is a map, and start, we have a start point, we have a goal here too, and then free space and obstacle here. And for let's make them dark. So it means that these are obstacles. These cells are filled with obstacles. Okay, so now till now we have, I think we have already studied in the last lecture, and also in the lab we did experiment also how to make manually a discrete map. So now it's time to do something with this map. So we have a discrete map, and this is the start. This is the start position we have here. So now how can we make a path from start to target position? So any ideas? How can we make, let's say our robot is here, how can our robot reach at point 2 without colliding the obstacles? Okay, one naive approach will be that move straight and then move left, but this is something very naive, and if the goal is different, then every time you have to develop a different strategy for that. So why not use some kind of clever, or at least some kind of basic search algorithm that can search a collision-free path from start to our target. One of them is the grid search algorithm. It's called wavefront algorithm. Wavefront algorithm is it's based on breadth first search graph search algorithm. We shall see later that how it works. But for now, you just focus on this grid and how this algorithm works, wavefront works. So what this algorithm does is, first it remains the target here. The target, it lets like, okay, this let it be 2. The target is 2, okay? But what it does, it looks for the neighboring nodes, okay? Look for the neighboring nodes, and for the neighboring nodes it look for and see which are obstacle free. For example, this node here, it's obstacle free, so robot can move here. And what it does is this wavefront algorithm make here put here 3, because this is one distance away from 2. Okay, so the distance between these two is 1. So, and I think I should also write how the distance also, this grid and its coordinates also. For example, write it with maybe blue. So this is 0, 1, 2, and 3. These are the coordinates of the cell. This is 0, 1, 2, and 3. Same like in matrix, you have row and columns. So these are the coordinates of the cells. Okay. So I was telling that it will start the algorithm, wavefront algorithm. It will start from your target. From here, it will start, and it will look for neighboring nodes. For example, it will look here, and here it was 0. It means it was free space. So what it did here, it put here 3. So after 2, it comes 3. So it put here 3. Okay, and then it will look at this node here. Again, it's free, and it will write down here number 3. Because this is also one distance away from one step away from your target. Okay, and similarly the algorithm look for other neighboring positions, neighboring cells, and it will put here in all the neighboring cells, it will put here 3 everywhere. There will be 3, 3, 3. So after 2 we have 3. The neighbors are 1, cell away from this cell, the target cell. So that's why there are 3. After that, after 3, you have to put 4. Okay, the algorithm will look for again the neighboring nodes of 3. It will look here, and this will look here. If it's a free space, and here it will look here, but it's not a free space, so it cannot go there. But here in these 3 cells, the algorithm can change. So first it will change here, and then it will change here and here, and these cells will have a value of 4. Here will be 4, there will be 4, and here also it will be 4. And these 2, the obstacle, they will remain unchanged. Okay. After that, after 4, we have now we will look again for the next nodes that are empty, next cells that are empty. So these 2 are the candidates, and the algorithm will here put, after 4 it will put here 5. So here will be 5, and also here will be 5. Okay, after that again the algorithm will look for neighboring nodes. From here it will look at this node, it's empty, and from here it will look at this starting node. So, and it will assign 1 plus number, 5 plus 1, now it will be 6. So the source cell will be assigned a number 6. So now here will be 6. This is our starting cell. Okay, and here it will also be 6. Okay, now we have 1 cell left, and then the algorithm will assign here is 1 distance away from 1 cell away from 6, so it will be 7. Here will be 7. Okay, so now it's you see that their behavior, it started from 2 and it expanded like neighboring cells 3 and then 4 and then 5, 6 and 7. So this is like wave like behavior. Okay, it's like wave has been started from at the cell 2 and it's traveling in every direction. Okay, and finally it reached at your start point also. So that's why it's called wavefront algorithm. So now the thing is, where is the shortest path? Because the purpose of this algorithm was to find the shortest path from start to target point, from this cell number 6 to cell number 2. So how we can now find the path? The next step of wavefront algorithm is that you have to follow the minimum number till the goal. So that's how it works. So what it will do, it will start from this start cell, okay, and then it will look on your neighbors, that either one of its neighbor is 7, other is 5. So it will always follow the minimum value neighbor. So from here it will go to 5. Okay, so once it reaches 5, now it has more option that it can go to this. On the right side there is an obstacle where it's not allowed to go, and on the downside it's 4, so it will go to 4. Okay, and now it has it has option, it has option to go to 4, either to 3 here, and it's also a 3 here. So here it depends upon now which connectivity has used here. If you have used this Fon Neumann connectivity, 4 connectivity nodes, then your robot will go like, your path will be like this. It can be like this, okay? But if you have used 8 connectivity, where the diagonal movements are also possible, then your robot will, or your path will go like this also, or it can go like this. So for simplicity, let's see that we have only 4 connectivity, and so the path will go like this from here to here, okay, and after that it will again look for neighboring nodes. Here it has a 3, and when both sides have same, so you can select anyone. So from here it will go this one here, and from here it has then options to go into 4 or 2. Of course the 2 is the minimum one, it will go to 2 here. So you have seen that that's how the path is made from the start position to the target position using wavefront algorithm. And this path is obstacle free, there is no collisions, and it's also the shortest path if you follow the 4 connectivity neighborhood, okay? But if you follow the 8 connectivity, then shortest path will be something like, I can show you. From like here to here, then here, and then here. So it will be something like this. Yeah, this will be shortest. But for 4 connectivity, I think this will be our shortest path, the one we have made already. Okay, so this was a wavefront algorithm. It's very simple algorithm to search shortest path in the grid. It's very easy to implement also, and yeah. Okay, so grid search. What are the some advantages of grid search and disadvantages? So grid search is appropriate for low dimensional configuration spaces. I mean, if the dimensions are less, if the robot have, for example, less angles, less motions, number of motions, or less degree of freedom, then these kind of a grid search is useful. But if the robot have high dimensional configuration, then these kind of algorithms they are not suitable. Okay, after that we have computational complexity of the path planner increases exponentially with the number of dimensions. This is also one important thing, is that the with number of dimensions, for example, for 2D, if you use it for 2D, it will have for example, a moderate computational complexity. But when you increase the dimension of the space, let's say you make it 3D, then you have more number of nodes. The number of nodes will increase, and the computational complexity, the time required to find the solution or to search the path, and the space required, the memory required, will increase exponentially. That's why these grid-based search or path planning or motion planning is not useful for higher dimensional problems. Then we have quad tree. This is one method they use to reduce the computational complexity of the grid-based search. For example, this is my configuration space. I have a grid here. 1, 2, 3, 4, 1, and 2. So 1, 2, 3, 4, 5, 1, 2, 3. So it has 15 cells, okay? But we have, let's say, obstacle is here. This is obstacle. So now what's going on here? Just to model one obstacle, one small obstacle, we have to make 15 cells. Okay, if the but one way is that it means that the more number of cells there are, then the more space it will require to save it in your memory, and also more time it will take to find a path, the more number of cells you have. So one way to reduce number of cells is using quad tree. How it works is that you have, I am using same configuration space or same map. Here we have, this is obstacle here. So this time what we do, we don't discretize this map into equal cells. What we do, we first divide the whole space into four cells, 4 big cells. Okay, so that's why it's called quad. Quad means 4. So we have divided the whole space into 4 cells, and then we look for where is the obstacle, in which cell the obstacle is located. And so it's the top right cell here. And now we shall divide this cell again into 4 equal cells. And again we shall look where the obstacle is located. Okay, I think this was not a... So from here we have divided it into 4 cells, and then we shall see where, again, which cell has obstacle, and we shall divide this cell again into 4. So that's why it's called the quad tree. And now if you don't go further, then you have how many cells you have? 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10, 11, 12. So you can see that even you don't need this inner one. I think I should remove this one. Okay, so this is, for this it's enough to represent, to model the location of your environment. So how many cells we have here now? We have 1, 2, 3, and this one is 4, and then in this 4 we have 4 more, so 8. We have 8 cells, and these cells can represent your obstacle. If you want to divide it, it can be like 12 then, or maximum it will be 12 cells, but let's say there are 8 cells to model this environment. And here we had 15 cells. So that's why this is the better, this is efficient quad tree method of making a model of the environment or making a grid. This is efficient because it requires less number of cells to model the environment. Less number of cells mean it will have it requires less memory, less space in your computer, and also it will require less execution. It will require less time to solve the problem or to find a path. Okay, now we have graph search algorithms. We have seen previously, in previous slide, we have seen the grid search algorithms, and now we shall see the graph search algorithms. So the first one is the breadth first search algorithm. You remember what are the graphs? Graphs were the combination or collection of nodes and edges. It's the points and lines that join them, that relate them. So how we can now, we have seen previously how we can find a path in a grid. But if we have given a graph, then how we can find a path in the graph? Let's say this is A, node A, and then we have node B, node C, this is node D, and this is node F. Okay, this is a graph. These A, B, C, D. It's okay, this is E. So these are the nodes, and the lines that connect these nodes, they are edges. So what we want to do is that we want to find a path from A to E. So E is our destination or target, and A is the start point. Okay, so how can we find a path shortest path between A to E? How can we do that? One way is using this breadth first search algorithm. This is the simplest graph search algorithm.